Okay, so now let me talk about some of the reasons why covering spaces are worth isolating as a definition and concept to study in its own right, and then prove kind of the first main result about them. So I'll say the goal of covering spaces, and understand that I'm just kind of inventing a goal to anchor this discussion, because how would you respond if somebody asks you what's the goal of linear algebra? Maybe it's just such a fundamental way of organizing information that's its own reason to study it. But I'll say that the goal for our discussions is, in some sense, to recover E from B, given a covering space, or relatedly, to classify covering spaces whose base is B, so over B. Or relatedly, to come up with new ones. And distinguish between two. So tell when two are different. Yeah, so this is kind of the goal, I suppose. So I feel compelled to remark, for those that are interested in more in algebra, I'll just say that this is a topological version of Galois theory, which is, if you don't know of it, it's a subject for examining roots of polynomials. And it does so by formally adjoining roots, looking at symmetries of the resulting algebraic data after adjoining the roots that fix the coefficients of that polynomial. And it's analogous to this covering space classification. So there's a main result theorem. I'll state it here in a simple case and then establish it again in a more general case. It's the unique path lifting property. And it's on this that all these classifications rely on. So let that be a covering space. So I'll write it out diagrammatically, and then I'll comment on it. So let this be a commutative diagram. So what is a commutative diagram of topological spaces like this? Well, this corner is the topological space, which is the closed interval. There's the base topological space, and a continuous map from the interval into B is precisely the data of a path in B. Here, that's just a point, and that point maps into the interval, selecting out the endpoint 0. A continuous map from a point to E is precisely just the data of a point in E. And to say that this diagram commutes means that, or what this diagram is a path in B together with a choice of an element in capital E over the starting point of that path. So I would draw this like if B is the circle and E is also a circle mapping to B by that 2-to-1 cover. And if, here's the interval, if gamma is the map that watches the path move around like that, starting there, ending there, 0 to 1, this is the map from a point that just selects out 0, and this is a choice of pre-image. There's 2 pre-images of 0, and this selects out one of them. Let's say that one. So this is a schematic picture, I guess, and an example of what this is abstracting. So let this be a commutative diagram. Then there exists unique continuous map from 0, 1, call it gamma tilde, into capital E, not any old one, but such that, and I'm just going to reference over here, such that this diagram commutes. In other words, if you do this followed by pi, that composite map from an interval to B will agree with the map gamma. And likewise, if you do this followed by gamma tilde, that will agree with gamma tilde not. That's the condition such that. I'll draw it in pictures. In other words, so that there's a map, a continuous map from this interval into this topological space. In other words, a path in here. Now, to demand that this upper triangle commutes is to demand that the path selected out by this gamma tilde starts at the already selected points in capital E. To say the bottom triangle commutes is to say that that path projects down to the given path already specified in the base. So the picture would be that. That's what gamma tilde is. So that's the assertion. Given a covering space and given any solid diagram, there exists a unique filler. So let's prove that now.